multiplied by the resistor, and we get a voltage noise. And then the voltage noise will convert into jitter through a mode that we call amplitude noise to phase modulation conversion. So let's take a look how voltage noise converts into jitter. Here we have a distribution shown for voltage noise, and it looks like a Gaussian distribution. Now the distribution doesn't need to be Gaussian, it could be bimodal or trimodal, but here we're just showing for simplicity voltage noise at the limit of plus or minus 1 sigma, which captures 68% of the population. So the error that we have in this particular case would be 100% minus 68%, or 32%. Now, generally speaking, that's a pretty bad error, so when we do an analysis for a real application, we don't want to use 1 sigma. We want to go out 2 or 3 sigma as appropriate for the error rate that's acceptable for that particular application. And that's decided by you if you're working with that application. But here we're showing 1 sigma statistics, and we can see that if we have a voltage noise defined by plus or minus 1 sigma, then we translate that down through the slew rate, we end up with a jitter, a corresponding jitter standard deviation of plus or minus j sub s, where the s is for slow slew rate. And we can see geometrically that as we make that edge sharper, we end up with a situation where we have much lower jitter. So the plus or minus j sigma sub j sub f, which is the fast slew rate jitter, is much lower than the slow slew rate jitter. And we can have a very simple equation to summarize this. The jitter is equal to the voltage noise divided by the slew rate. And we can see that the voltage units cancel out and the seconds comes on top. So jitter's measured in seconds. And this is a nice way that we can very simply think about computing jitter from an edge. And so typically, as I mentioned before, the receiver has a specific switching threshold. We want to make sure we emulate that here for our choice of our threshold voltage. And that's the location on the rising edge or falling edge of the waveform that we want to capture jitter. So examples of where we can have fast and slow slew rates. Well, if we have weak drivers, that'll slow down the signal. If we have high capacitance loading, that'll also slow down the signal. If we have long lines or lossy cables, that will also slow things down. And generally speaking, this identifies one way that we can actually see to improve jitter, which is to sharpen up the edge rates. So that's one key thing we can start to see on how to minimize jitter. We can see clearly here, we can minimize it by sharpening up those edges. Another source of jitter is electromagnetic interference, which we can define as undesired radiated or conducted emissions from an external source. So here we're showing an external source. This is, for example, it could be a switching power supply, could be other reasons. And then there's usually a radiating path if it's radiated emissions, and that can couple on to our victim waveform. And if it happens to couple on in the wrong location, then we can see that we have jitter as a result. Crosstalk is another area that can create jitter. In this example, we have an aggressor and we have a victim lines. And we can take a look at two scenarios. One is a microstrip and the second is a strip line. So in the microstrip case, we have two conductors sitting on a dielectric over a plane of constant voltage, which could be power or ground, for example. Now let's imagine that we have a scenario we have logic level 1 on both of these conductors, and then some instance later, one of those logic 1s flips to a logic 0. And we can see the electric fringe field lines change their pattern. And in doing so, they change their mutual capacitance, inductance between the two conductors. And so they can induce currents and voltages into each other, which can add to and degrade to the signal. And that's what we see over here. In the microstrip transition line, we can see differences depending upon the fringe field lines, which is a function in this case of the data pattern. If we move instead to a strip line case where we have dielectric above and below both conductors and planes of constant voltage, for example, power and ground above and below the conductors, then the electric fringe field lines are fairly consistent with the data pattern, and we end up with a much better jitter scenario. on the victim line. So microstrip lines aren't necessarily bad. It really depends on your application. For short distances, they're generally okay, but if you're going to route over appreciable distance, generally speaking, strip line is a better approach. It does have the downside of requiring more layers, so there's more cost for the design, but typically this is employed in high-speed designs where jitter is critical. A lossy medium is another source of jitter. In this case, if we look at the electrical side, we can see that as the frequency component in the signal goes up, that frequency component has a higher loss compared to lower frequencies. A very common material used for PCBs is a FR4 insulator, although other insulators such as Rogers and other materials could be used. But they all suffer from the frequency-dependent loss. So if we look at the ideal waveform, shown in gray, it has nice sharp edges, rising and falling, and flat logic levels. And then we slice the actual waveform at the midpoint, shown by the threshold voltage, because that's where we want to measure jitter. And let's compare the situation where we have a long string of logic 0, followed by logic 1, and then a logic 0, and then we have a long string of logic 1s, followed by logic 0, and then finally a logic 1. And if we compare the first rising edge with the last rising edge, we can see that the first rising edge crosses at a value of T1, and the last rising edge has a head start. Because of the capacitive effect of the frequency-dependent loss, we see that the signal itself actually has a little bit of a head start before it turns around and goes back up and crosses the threshold voltage. And as a result, the value of T2 is less than T1. And in fact, because T2 does not equal T1, we therefore have jitter. And here we're measuring time interval error jitter. It's the variation of a rising edge with respect to its average or ideal location. On the optical side, we also have a frequency-dependent loss characteristic, although we have a couple local minima here at 1330 and 1550 nanometer. And so that's generally where we like to operate our lasers. And so whether it's a laser itself or a laser diode and that LED, there are always multiple wavelengths that come out as a light source. You never just have one wavelength. And each wavelength propagates through the optical fiber at a different velocity. And so some of those wavelengths get out sooner than others. And that creates this chromatic dispersion effect that you see. This pulse looks like it's actually arriving a little bit sooner than the electrical equivalent side due to chromatic dispersion. And in this case, where we have the same data pattern with a long string of zeros followed by 1, and then the symmetrical case with a long string of 1s followed by a logic 0, we can compare T1 with T2, and again, the T2 is derived from a waveform that starts moving back up before it's hit the logical low level. But in this case, it occurs before the ideal edge instead of after the ideal edge, and so by symmetry, we see T2 is equal to negative T1. But again, the fact that T2 does not equal T1 means that we have jitter, because that means that there's going to be a variation of where that rising edge crosses the threshold voltage. Voltage droop and ground bounce are two more sources of jitter. On the left-hand side, we see an ideal power supply with an ideal load. In practice, you're not going to have an ideal package. There's always going to be some inductance from the lead frame or the bond wires, and through this change of current, it's going to give rise to this voltage droop if we're analyzing the bond wires on the VDD node. If we're analyzing the bond wires on the ground node, then it's going to create a similar situation, but we call that ground bounce. And because it's a time-varying voltage across the load, if there's any transistors in that load, the propagation delay of a signal passing through the transistor is actually a function of that voltage. And if that voltage is varying in time, the propagation delay is also going to vary in time. And that's just another way that we can define jitter. We can consider jitter to be the variation of propagation delay. So any variation of voltage across this active device or transistor is going to create jitter as well. So those are some common sources of jitter. In this next section, let's take a look at different types of jitter. And when I say types of jitter, I'm essentially going to define the three most common types of jitter. But a quick note, there are many standards in the industry. The industry is actually quite fragmented, and there's no universal standard defining jitter. So different standards are free to choose the same terminology for different types of jitter, or slightly different definitions. So if you're working within a particular standard, you really have to understand how that standard defines jitter, even though they may use the same terminology as some other standard. Here we show the definition of period jitter. Period jitter is fairly simple to understand. Its definition is the variation of any one period from its average value. So to calculate period jitter, you take the instantaneous period and you subtract from it its average value. Cycle-to-cycle jitter is the variation between two adjacent cycles. The only thing tricky here is that the most common way people measure cycle-to-cycle jitter is using the JEDEC standard JESD 65B, and that introduces absolute values. So it's taking the absolute value of the difference between two neighboring periods. And when you do that, you end up with all positive numbers, and it's a one-sided distribution. Time interval error jitter is the more complicated of the three. So time interval error jitter is defined as the short-term variations of a digital signal's significant instances from their ideal positions in time. So this is a more complicated way to express the variation of a timing event definition that I gave you earlier. And to analyze this, we need a reference waveform, and that's partly what makes it more complicated. So when we're talking about short-term variations, what we mean is greater than 10 Hertz, as defined by the ITU standards. So jitter variations that are less than 10 Hertz, we actually put that into a bucket called wander. But greater than 10 Hertz, we're going to call that jitter. That's all that the short-term variation means here. And what does the digital signal's significant instances mean in this situation? Well, the significant instances for measuring jitter are the rising and falling edges. And that's because where we have the threshold voltage that intersects the waveform, that's where we actually measure jitter. And then compared to the ideal references, ideal positions in time, that simply means that we require this reference waveform in order to measure jitter in the observed waveform. And the reason that time interval error jitter is a little more complicated is because it raises the question, where do we get the reference waveform? And we'll show that in another slide or two. But strictly following the definition, what we need to do first is calculate the time error as the difference between the observed threshold voltage crossing minus the reference threshold voltage crossing. And we have to make sure we get the polarity correct in the time error shown here. And then we can define the skew as the average value of time error. That'll give us the DC offset. And then we calculate the time interval error jitter as the variation around that skew. So to calculate that, we simply calculate the instantaneous time error value minus the skew value. And that gives us the variation around the skew. So to help explain this time interval error definition, let's go through a thought experiment. Let's suppose we have a 100 megahertz oscillator, and let's suppose that the oscillator has no jitter on it. Or we could say equivalently that the jitter on this oscillator is much lower than the jitter on the device under test that we're trying to characterize. And so the question is, what is the TIE jitter output by the DUT? So the DUT is entering channel 1, and the reference, or our oscillator, is entering channel 2. So I've shown some example waveform here with 13 periods, where channel 2 is our reference oscillator, and channel 1 is actually our device under test. And so since we need a reference in our TIE definition, we have that as the XO in channel 2. So we can calculate the difference between rising edges here, and we call that difference the blue value of 130 in the first rising edge and 195 in the second rising edge, and so on. And then from that value, we need to subtract the value of skew. So we can take all of those values here, put them in the numerator, add them up, and there's 13 rising edges shown here. So the average value happens to be 200. So we take that 200 and we subtract it from each of the time error values, and we end up with a value of 70 femtoseconds. And that 70 femtoseconds is represented by It's actually negative 70. So that would go into this bucket down here and represent a value of 1 on the y-axis. So there's one occurrence that falls between minus 60 and minus 80. And we can, if we take 13 edges here, we can build up this distribution that we show here. Ideally, we want to measure a lot more data than 13. We want to do millions of edges. And then we end up with a really nice looking distribution that's smooth. But for the sake of discussion, I just wanted to highlight the logistics of how we calculate this distribution. And on the next slide, we take this distribution and we're going to calculate the peak-to-peak value, which is the most positive deviation minus the most negative deviation. And that comes out to be 196 femtoseconds peak-to-peak. And we can also calculate the peak value as either the larger of the most positive deviation or the absolute value of the most negative deviation. And we end up with a peak value. And finally, we can calculate the RMS by computing the standard deviation. And so that standard deviation equation is shown here. This actually should be the denominator of 13 because that's the population. But we're going to take the instantaneous value of jitter minus the mean value. We're going to square that. We're going to sum them up, and we're going to divide by the population of 13 and take the square root. And when we do that, we get 48 femtoseconds. Now, you might ask, why are we labeling it as an RMS? Actually, the RMS equation itself is different, but the way that it's different is that the RMS does not include the mean. If we get rid of this term, then the equation for RMS is exactly the same as shown here, but without that term. Now, what's interesting is that the TI jitter mean value is 0. And the reason that we can label this as an RMS value is because this mean term is actually 0. So you might ask, why is the mean 0? And that's because if there were a mean, it would show up in the skew value that we subtracted from every instantaneous value of time error, and that's what gave us the time interval error jitter. So it took me a long time to figure out that the way that we label this as RMS is actually fine, because when it comes to TI jitter and other types of jitter, the mean should always be 0. There is one exception, which is cycle-to-cycle jitter, because in cycle-to-cycle jitter we actually have the absolute value, which means the mean value is different. So for all other types of jitter, the mean value is 0 except for cycle-to-cycle jitter. That's just one caveat we have to remember. But otherwise, we can label the standard deviation as an RMS value here. So the key point here is that when we measure jitter, we want to measure lots of different values, and then we measure a distribution from all those values. And then from that distribution, we can pick off a peak-to-peak, or a peak, or an RMS value. And so we have 3 metrics we can extract from a distribution. And whenever you measure jitter and quantify it from a distribution, we always want to keep in mind these statistical units is part of the actual unit. So we don't want to forget those, because if we do, we're missing valuable information, and we don't know how to interpret that jitter number unless we have those statistical units attached to them. So that's very important. Okay, so those cover the 3 most common types of jitter. The next section will talk about where do we use these different types of jitter, and more importantly, why do we use those types. And so we talked about 3 types of jitter, and we're going to cover several different applications that are very common in the industry. And it's important to keep in mind that for any particular interface, there's really only 1 or 2 types of jitter that are critical. The rest of the jitter we don't really care about. But we have to understand the application to understand which type of jitter is important. And then once we understand that, we go to the data sheet and find the relevant jitter. We don't work the other direction. In other words, we don't start at the data sheet, understand what's on the data sheet, and try to fit that to our application. That direction doesn't work. We always begin with the application and what the application requires, and then go to the manufacturer and find the relevant information. So let's take a look at data converters first. When we're looking at data converters, we have a sampling clock, and the rising edge of that sampling clock is going to sample the voltage. So if there's any jitter on that sampling clock, it's going to translate into a voltage error, delta V. So it's really important to keep sharp edges to minimize jitter on the sampling clock, and this kind of works in the opposite direction of what we talked about earlier, how voltage noise converts into timing noise. This is actually the opposite direction. This is timing noise converting into voltage noise. And you'll notice the error voltage delta V is actually the same equation shown here for what we used to call V sub n, because this is our slew rate and this is our TIE jitter value. So this is very commonly used in the data converter industry to minimize sampling errors, to keep a really sharp edge. And they have an equation here for signal to noise ratio that involves the highest frequency component in the analog signal. We call that F sub n. That's the highest frequency that you happen to care about in your application. You set that value as F sub n. And then if you have the value of the TI jitter expressed as an RMS, for example, from the distribution that we discussed earlier, you multiply those two times 2 pi. You take negative 20 log of that number to get it in dB, and that's your signal to noise ratio. So that's a very useful property. You can also work backwards. If you know the signal to noise ratio and you know the highest analog frequency of interest to your application, you can back calculate the value of TIE jitter. Okay, so data converters is really important to have low jitter on the sampling clock. The next application is synchronous logic. Synchronous logic is really dictated, the timing is dictated by setup and hold time equations, because what you don't want is you don't want a jitter clock to come around and sample the data signal before it's settled into the correct value. So in this example shown here, the data is sampled a little bit too soon and ends up with the wrong value. So to ensure that we only sample the correct values, there's a setup and hold time equation that digital designers have to adhere to. And part of that setup and hold time equation is period jitter. So period jitter is built right into those equations. So anytime that you have a digital logic, then you're going to worry about period jitter. You're going to need to use period jitter. The next thing is that clocks driving phase lock loops. Well, in phase lock loop, there's always this feedback path. So you take the output node and you connect it back to the input, which is your phase detector block. Your phase detector is looking at the phase of your input reference here, and it's comparing it to the phase of your feedback, and it's calling that delta phi, and that's your error signal. And the loop is operating off of delta phi in order to minimize that phase difference delta phi. So that's the error signal that you're trying to minimize by closing the loop. And so the feedback loop adjusts to minimize delta phi. Now, if you look at this from the phase detector's point of view, or it has two inputs and it's looking at one input with respect to another input and creating this delta phi, that actually, when you think about it, is our definition of time interval error jitter, because the input serves as the reference and the output serves as the observed waveform. And we're looking at the rising edge of the observed waveform with respect to the input reference edge. The phase detector itself is a digital block, and so it has a reference threshold voltage, and so it slices these waveforms at the midpoint or wherever that threshold voltage happens to be set, and so it's measuring exactly time interval error jitter in this PLL architecture. So any PLL is concerned about time interval error jitter by definition. Another consideration for clocks driving phase lock loops is how stable the clock is. In other words, if the clock has too much high frequency content in its jitter, then the PLL won't be able to lock to it. So in order to bound that, in order to prevent that scenario from happening, they use cycle-to-cycle jitter, because cycle-to-cycle jitter has the property that it attenuates or it filters the low-frequency jitter content. So any low-frequency jitter gets filtered as if the cycle-to-cycle itself, the definition of cycle-to-cycle jitter when it gets analyzed mathematically, it's actually a minus 4 dB per decade high pass. So the low-frequency content gets filtered at minus 40 dB per decade. So cycle-to-cycle jitter can be used as a figure of merit for high-frequency content, and on some data sheets for microcontrollers or microprocessors or large ASICs, if there's a clock input that drives an internal PLL, that clock input very often will include a cycle-to-cycle jitter spec just to ensure that the integrated PLL can lock onto that clock. I guess we can divide the world of buses into parallel buses and serial buses. Parallel buses take a clock and distribute it to either end of the link, and they time data onto the link using synchronous logic. So if each link has x bits per second and there's n links, then the total throughput is n times x bits per second. Because the data is timed using synchronous logic, and synchronous logic requires setup and hold time equations that use period jitter, then period jitter is critical for parallel buses. On the other hand, serial buses are based on a phase lock loop technology. So you have a clock that's driving data onto a channel using a phase lock loop. And therefore, the relevant type of jitter for that clock is time interval error jitter for the reasons that we discussed earlier. And in this case, there's only one link here, and that link throughput is n times x bits per second. So the relevant type of jitter for serial buses is time interval error jitter. So that's it for the class. The key points are that the definition of jitter, to keep in mind, is that jitter is the variation of a timing event, and it's how you define that timing event that defines the type of jitter, or the definition, or how you measure that jitter. It's really how you define that timing event, and jitter is really concerned about the variation of that timing event. And keep in mind that only one or two types of jitter matter in any given interface. If you're working with parallel buses, you care about period jitter, and serial buses care about time interval error jitter. And the key point, the last bullet here is the key point, that really try to understand your application from the point of view about what type of jitter it cares about and why. And hopefully the earlier slides gave you some understanding and some insight into how jitter gets mapped into different applications. And if you can't find that particular type of jitter on the clock manufacturer's datasheet, then contact the manufacturer to find out more information. So that's it for the class. I really like to thank you for your time. I hope you enjoyed it as much as I enjoyed teaching it, and I hope to see you again. And if you have any questions, we'd love to hear from you. Thanks so much, and have a great day.
Okay, that ends part one of the presentation. That was very interesting. Thank you, Gary. Now we're going to get ourselves set up for part two of the presentation. As a reminder, after part two, we will have a live Q&A with Gary. So don't forget, you can still submit questions anytime using the chat box tab on your right-hand side of your screen. Let's see. Gary, are you set to go?
Yes, I can. Can you hear me?
I can hear you, yeah.
Perfect. Okay, well, I thought we would go into a quick summary of how we could actually apply this class in one slide. Most of you probably work with systems, and here I'm showing a hypothetical block diagram just to show interfaces, and I've identified interfaces with arrows here. And if we work around, starting from the lower right, the 156.25 megahertz clock that's driving the PLL, the question is, what type of jitter do we care about in each one of these interfaces, and why? So the 156.25 megahertz, since it's driving a PLL, and that would be time interval error jitter as well as cycle-to-cycle jitter. So those two types of jitter would be important here. The arrows feeding to the right side of the PLL is your high-speed data. So that'd be operating at 10 or 100 or 200 gigabit per second. That's high-speed data, and that's a serial interface. So the type of jitter on those interfaces would be time interval error jitter as well. Now the 16 line parallel bus between the processor and the SerDes, since that's a parallel bus, those interfaces would be concerned with period jitter, primarily for setup and hold time calculations. To the left of that, we have a 25 megahertz driving a PLL. So that again would be TIE and cycle-to-cycle jitter. The 66 megahertz driving the processor. Since that's driving synchronous logic, you'd care about period jitter. The 24.576 megahertz driving the data converter. Since it's the data converter, we would care about the time interval error jitter. And then lastly, the 200 megahertz, which is the top arrow, we don't know what it's driving because it hasn't been populated yet. Therefore, we don't know what the jitter requirement is for the output of that clock generator for 200 megahertz. So this is essentially summarized here on this slide, but that is the thinking process that I hope that you can walk away with this class and use in everyday life. In addition to helping you with what you can use in everyday life, we wanted to provide some resources. One of the resources is the Timing Essentials Learning Hub, which we have at learning.scitime.com. If you like this content, we have a whole lot more available on this website that is free, just requires registration, so we encourage you to check that out. We try to cover all the fundamentals of timing, as well as some of the product-specific features and benefits we have. We also provide a free software download that you can install in your your Apple or your Windows machine. This is called SideTime Studio, and it's free software that post-processes phase noise. So if you need to filter phase noise to emulate the end application, if you want to integrate the phase noise to create phase jitter, if you want to save the results in the PDF file, and so on, you can do all that with this easy-to-use software. And we also have the ability to, for our clock generators, for you to download the GUI, can create a configuration file and upload that configuration file into our Lab Anywhere, which is an online bench that we have, and it's actually connected to real instruments that will select a part and program it according to your instructions. And then you can actually measure the phase noise and other aspects of that device, and it can be done. So instead of getting a val board and going into the lab to evaluate it, you could simply just configure the part using our GUI, send in the evaluation, the configuration file, and get the results as if you had a lab, but it's all done through this Lab Anywhere tool. We also have a 4-minute clinic video if you're interested in phase noise. This will tell you how to visually inspect the phase noise curve and determine the region of the phase noise that dominates the phase jitter value. When you integrate the phase noise, you get a phase jitter value, and you'll be able to visually inspect the phase noise to determine which region of the phase noise curve is limiting or dominating that phase jitter. So it's a very interesting thing that you can walk away with and be able to eyeball phase noise, which is very useful. We also have a lot of free online calculators, all the way from jitter calculators to budgeting jitter, determining eye closure, and so on. So we have these and a lot more available. These are just the jitter ones, but we have additional ones for stability and other aspects. So we encourage you to look at that. We also have a lot of application notes that I'm showing here, the relevant ones for jitter. The first one talks about how we define jitter. The second one is very useful if you're doing lab measurements. It explains how to set up a real-time oscilloscope to measure jitter. The third one is really very useful if you're working with high-speed serial data interfaces like 100 gigabit Ethernet and so on. This one is based on a DesignCon talk that I gave this year, and it goes into depth about the recommended way to analyze modern high-speed SerDes. And then we have another one that's very detailed for PCI Express reference clocks, how to show jitter compliance using a phase noise analyzer, which kind of goes behind the scenes of the PCI SIG electrical work group and how this phase noise compliance test was created. It gives you some background information, it gives you some insight into why it is the way that it is. And finally, the last one is about removing oscilloscope noise from jitter measurements, which I don't really expect anybody to go out there and start coding to remove these, but a lot of the oscilloscopes are starting to adopt this methodology as we go to higher data rates to remove the jitter introduced by the instruments. And if you want to learn how they're doing that, it's a pretty simple process. So I recommend that you read that. It's very interesting. A little bit hard to code though, but it's easy to understand, at least conceptually. And we also have a lot of application briefs discussing many different areas that timing is used across the industry. Hopefully you can find something here that relates to what you do. And if you open these briefs, you'll be able to understand the block diagram and how timing provides signals into that and how side time might be able to help you. We also have a full portfolio of timing products. SideTime is 100% focused on timing. We provide resonators, oscillators, clock devices, jitter attenuators, and network synchronizers, and we're just 100% dedicated to timing. So we've listed some of the categories here to provide quick references to you. And some of those are listed here as a product selector guide for some of the more recent products that we have. This one is focusing on differential oscillators. We also have clock generators and jitter cleaners, all with various levels of jitter and configuration abilities. And that's it for the references section. I think now we can move to Q&A.
Excellent. Yeah, thanks, Gary, for that great presentation. We already have several interesting questions, but I want to let our audience know that it's not too late. There's still time to pop a question into the chat if you want to do that. So Gary, are you ready to go?
Yes.
Okay. First question, interesting. Is phase noise the same as jitter?
So phase noise is a very popular